What's up everyone, my name is Rohak, and in today's video, we're going to be exploring the support vector machine algorithm in Python. With real-life applications ranging from protein folding detection to handwriting recognition, the SVM approach can be used to tackle all sorts of regression and classification challenges. By mapping data to a high-dimensional feature space, SVM is able to categorize data points and separate them linearly at a much faster pace than state-of-the-art approaches. Throughout this tutorial, I'll be taking you through all of the essentials needed to implement the algorithm in Python, all within the span of just a few minutes. Well, enough of me talking. Let's get started. Welcome to the programming section of this video, where we'll be implementing the support vector machine algorithm in Python entirely from scratch. As always, if you want to follow along with the tutorial, the link to the Kaggle dataset we will be using can be found down in the description below. Feel free to check it out. With all that aside, let's get started. To start off, we will first import pandas for data frame manipulation, as well as seaborn and matplotlib for data visualization purposes. Next, we need to read in our breast cancer data and print out the first 5 rows to the console. So here, we do this by calling the readCSV function of pandas and specifying the file path of our CSV as a parameter, and then finally, we call the head method on our data frame to view the first 5 rows of our dataset. So here, if we click run, we yield the following data frame. And here we can see 5 independent variables being attributed to a dependent variable of diagnosis, where a value of 0 represents there being no risk of breast cancer, and a value of 1 represents a positive test for breast cancer. Now, if we want to print out various statistics about each attribute value and feature in our dataset, we can simply call the describe method on our data frame. So here, if we click run, as you guys can see, this method call yields a data frame with all sorts of statistics for each column in our dataset, ranging all the way from the standard deviation to individual percentiles. To check for any null or missing values, we can call the isNull method on our data frame and view the sum total of missing values for each column by using the sum method. So, if we run our code, we see that we get a total of 0 for all of our columns, which means that we have no missing values to handle. With our data preprocessing stage complete and finished, now comes the fun part, where we enter the fascinating world of data visualization and model building. Well, what are we waiting for? Let's get started. To begin, we'll first model the relationship between mean area and mean smoothness, which can be easily done by using the scatterplot function of seaborn. So here, in our method call to scatterplot, we pass in our mean area column for x, our mean smoothness column for y, set our hue to diagnosis, and assign the data hyperparameter to our data frame. In regards to the hue parameter in particular, it's responsible for determining which column decides the kind of color for each plotted data point. This should all make much more sense once we actually visualize our scatter plot. For the time being, let's add some helpful axes labels and a title to our plot for increased readability. So here, as you guys can see, I've added a title, an X label, and a Y label so that someone who isn't exactly familiar with our data can still understand our scatter plot. So if we click run, we yield the following scatter plot, with mean area plotted on the x-axis and mean smoothness plotted on the y-axis, with data points having a diagnosis value of 0 colored in dark blue, and those with a diagnosis value of 1 colored in bright orange. However, also notice that there is a clear decision boundary formed on the scatter plot. In other words, we can see a clear partition that separates breast cancer positive points from breast cancer negative points. So we can ultimately conclude that a support vector machine is a suitable algorithmic approach for modeling the relationship between the independent variables of mean area and smoothness and the dependent variable of breast cancer diagnosis. Perfect. Now, to begin our model building process, we can start off by importing the SVC classifier from ScikitLearn's SVM module and the train test split function from ScikitLearn's model selection class. Next, we can partition our data into X and Y subsets by assigning a variable called xData to the mean area and mean smoothness columns, and by assigning a variable yData to the diagnosis column in the data frame, which, once again, is the variable we're trying to predict. With that aside, we can retrieve our x and y trained test sets by calling the train test split function with the x and y data we generated earlier and specify a test size of 0.2, which means that our training sets will consist of 80% of the data and our testing sets will consist of 20% of our data. Next, we can create our support vector machine classifier by simply declaring and instantiating a new SVC object and storing the result in a variable called model. Next, we can fit our classifier and train it by using the x and y training data that we generated previously. Additionally, if we want to model the decision boundary through our data, we can simply import the plot decision regions function from the plotting module of the MLExtend library. After setting the size and dimension of our plot to 17 by 15, we can now call our plot decision regions function with our x and y train sets passed in as numpy arrays and our CLF parameter set to our SVM classifier. So if we click run, we can see that the decision boundary is clearly visualized, with the orange triangles over here representing data points with a diagnosis value of 1 and the blue squares over here representing data points with a diagnosis value of 0. To make predictions with our newly created support vector machine classifier, we can simply call the predict function with our x test set passed in as a parameter. This method involves our model making estimates for the diagnosis values based off of x input data that it hasn't seen or encountered before. So if we print out our predictions, we get the following result. And here we yield a list containing all of our model's predictions, which are either represented as 0 or 1 since our diagnosis value is binary in nature. Additionally, if we want to gauge the accuracy of our model on the testing data, we can simply call the score method with our x and y test sets passed in as parameters. Running our code, we see that we get a great accuracy measure of roughly 90%. Finally, to finish off our deep dive into the support vector machine algorithm, we can plot a confusion matrix to see where our model made the most misclassifications, which are denoted as false positives or false negatives. So to do this, we first have to import the plot confusion matrix from ScikitLearn's metrics module. After this, we can call the function with our model and XY test sets passed in as parameters. Optionally, I also specified the color map or CMap parameter as blues, since it makes the confusion matrix easier to visualize and understand. Awesome, so if we run our code, we get the following confusion matrix. And so on the x-axis, we have our predicted label, and on the y-axis, we have our true label. So hopefully now that we know where our model made the most misclassifications, we can choose to improve it in the future. And just like that, we have implemented the support vector machine algorithm from scratch in Python. As always, if you would like to view the full Jupyter notebook for convenience, I've included the GitHub link in the description below. Feel free to check it out. Aside from that, thank you so much for watching. I hope you are able to learn a thing or two, and as always, I will see you in the next one.